In Lesson 3.1, we will be discussing exponential functions. In Video 3.1.7, our learning target is for students to solve problems involving exponential growth and decay. In Example 7, we are dealing with deer population. The table shows the population growth of deer in a forest from the year 2000 to 2010. If the number of deer is increasing at an exponential rate, identify the rate of increase and write an exponential equation to model this situation. What they've given us here is the deer population in the year 2000. There were 125 deer. And in 2010, the number of deer was 264. What we're asked to do is write an exponential equation to model this situation, or to represent this situation. That's what model means. Okay, we want to write an equation that we can use to predict the deer population in future years, or within the years 2000 to 2010. Now, what we're going to do is we're going to use the equations that we are given before, and in this case, we need to figure out what the rate of increase is. Okay, in that case, that's R. We need to find R, our rate of increase, and then come up with the exponential equation to model the situation. We're going to go ahead and do this on the next slide. So given that our growth in our deer population is not continuous and we're trying to find our rate of increase, we're going to use the function or equation formula n equals n0 1 plus r to the t. Okay, so we have n sub 0 here. That's our initial population. So in this case, our initial population is 125. That was the population of the deer in 2000. There was 125 deer. And in 2010, there were 264 deer. Now, since our initial population was 125, then for n, t years later, our population is 264. So this is our population 10 years later. We have 1 plus r, and then t is going to equal 10, since I've plugged in 264, which is the population 10 years after our initial population was 125. So what we're looking for here is we're going to try and find r in this problem. What is our rate of increase exponentially over the course of those 10 years? Okay, so in order to get rid of, since I'm multiplying 125 times 1 plus r to the 10th power, I'm going to start by dividing both sides by 125. These 125s cancel out, and 264 divided by 125 is 2.112. And that's equal to 1 plus r to the 10th power. Now we need to undo the 10th power here. So there's two ways we can do that. We can either raise both sides to the 1/10th power, or take the 10th root of both sides, because the 10th root undoes the 10th power. Well, the 10th root is the same as the 1/10th power, so I'm going to raise both sides to the 1/10th power. The 1/10th power undoes the 10th power, and I'm going to take 2.112, raise it to the 1/10th power, and I get 1.077629301, and that's equal to 1 plus r. And if I want to finish getting r by itself, I'm going to go ahead and subtract 1 from both sides. Since I'm adding 1 to r, to undo that, I would subtract 1 from both sides. And r is, if I round to the nearest hundredth, or actually nearest thousandth, I would get 0.078. Tens, hundreds, thousandths. And that as a percent, that's my decimal. As a percent, if I move my decimal over, that is an increase annually of 7.8%. Now, what we need to do is write our model, which is basically go back and rewrite this equation with our rate and our initial population so that we can use this equation to predict the population of the deer in any year that we wish. So going back to our original equation or formula here, we said our initial population was 1.25, and here we're going to get 1.078 to the T. And that's rounding our R value there. We're taking 1 plus the value of R. R was 0.078 approximately. So we would go ahead and add 1 to that to get 1.078 inside of our parentheses. This is our model, our mathematical model. It allows us to use any value of T and find N, which is the number of deer, T years after 2000. In part B, we're looking at another deer population question. The table shows the population growth of the deer in a forest from 2000 to 2010. We're asked to use your model to predict how many years it will take for the number of deer to reach 500. Now remember, we already found our mathematical model in part A. That was N. N is for number of deer. N equals 125 times 1.078 to the T, right? Our rate of deer population increase was 7.8% approximately. And we want to figure out how long T is time, how long will it take us, or in what year would our deer population reach 500? We need to figure that out. So here's the possibilities here. We could type in Y1, we could type in our model from part A, which allows us to predict the number of deer in any year T, when T represents the number of years since 2000. And we want to know when our Y value for that model will reach 500. So essentially we're using Y in place of N, and on our graphing calculator we'll use X in place of T. So we're going to go ahead and graph these two functions. We're going to get an exponential function here, and then just a constant straight flat horizontal line at 500. And we want to know where those two functions intersect or equal each other. So go ahead and type in these functions into Y1 and Y2 on your calculator and calculate where the two functions intersect each other. If you use an appropriate window here, the window that the graphing calculator uses is -5 to 50 with a scale of 5 on the x-axis, and from -25 to 600 on the y-axis using a scale of 25. And what you're seeing, like I said, the y equals 500. That would be our y2 function. And y1 would be this exponential curve here. If you calculate where those intersect using the calc menu, which is under second and trace, you'll get the calculate menu. Option number 5, I believe. Option number 5 is intersect. And all you have to do is place your cursor using the left and right arrows on your keypad. Place your cursor near the point of intersection and press enter 3 times, and it should give you the intersection. Now, our population here is 500, approximately 18 and a half years after 2000. So if we want to figure out in what year this would happen, it would probably be sometime in the year 2018. Because remember, our initial population of 125 was in the year 2000, and in the year 2018, like in a half, so maybe in June of 2018, we would have a population of 500. It would take us approximately 18 and a half years for the deer population to increase to 500 deer. In real world example 7, guide and practice, this time we are dealing with rabbit population. And it says use the data in the table and assume that the population is growing exponentially. Identify the rate of growth, your R value, and write an exponential equation to model this growth. They're giving you the table of values here. Your initial population is 4.5. So actually 450, because that population is measured in hundreds. So you would take 4.5 and multiply by 100. And 210, in the year 2010, you have 6.600, or 6.6 times 100 is 660. What you want to do is figure out what the equation is and the rate of growth. The equation is also referred to as a mathematical model. So go ahead and calculate what you think your equation is and what your rate of growth is. Rate of growth you have to find first before you write the model. And then submit your answer A, B, C, or D. In part B of real world example 7, we're still dealing with the rabbit population. Using the data in the table from part A and assuming that the population is growing exponentially, use the model you found in part A to predict in which year the rabbit population will surpass or be greater than 850 rabbits. You have 4 choices, A, B, C, and D, and select the correct response and press submit.